without further ado,
in this video, we're going to quickly run through the names of the 8 most common 3D shapes that you need to know, which we also sometimes call solid shapes. First though, we need to quickly cover how to label the different parts of 3D shapes. If you remember 2D shapes, like a square, they have...
Are you guys doing okay? The British accent's not throwing anyone off. It's okay if it is, but I'm assuming it's not, but I don't want to assume. I kind of, of course. All right, cool. So, all right, sorry, I'll be quiet.
Corners and sides. But things are a bit different for 3D shapes, like this cube. Instead of corners, they have vertices. And if you're just looking at one, we call it a vertex. Then they also have edges, which are these lines in between the vertices, and faces, which are the flat surfaces between the edges.
Yep.
So if we look...
So this is kind of the first big piece that we need to look at. So I'm assuming everyone's feeling pretty good about where we've been and where we're talking, where we're going, I guess I should say. Just for fun. So we've been in the land of two-dimensional shapes, right? These are our polygons. And so for the most part, right, we know that we have these two pieces. Oh, that's really fun. So hopefully everyone feels good about this. So of course the corners, right, are the places where the sides meet, and we know, right, that it forms what we call it an internal angle. Why is this on white? I was like, what is it? All right, so that's really light, but so if we move from our two-dimensional shape that we can recognize based on corners and sides, okay, and we move into the realm of three-dimensional shapes or three-dimensional space, what we call the corner, right, on a polygon, what can we think of as the corner in kind of 3D land? Like a vertex, an edge, or a face? A vertex. Does everyone agree with Kevin? Is that feeling good? Hopefully it doesn't feel hard. But really on a 3D shape, you could think of the vertices or the vertices as corners as well, if that helps you remember, right? So basically kind of the same thing, except here we have, right, a two-dimensional corner. Right, so a vertex is basically, right, our 3D corner.
Or a point?
Yeah, it could be, whatever forms that, right, where edges are coming together to form some kind of point, knob, corner, whatever you want to think of it as. Good. So then what about our 2D shaped sides? What does that correspond to? Edges or face?
Would be a face, wouldn't it? Or edge.
Edge, yeah. So really what I might be jumping a little bit, but right. So here's our edge, right? So when we have a side, right, in a 2D shape, that becomes, right, our edge. So now, where the faces come together, right, create edges, and then, right, basically the top and the bottom of the edges are forming vertices, corners. And then we don't really have a word, right, to describe kind of what the face looks like in the 2D shape. Does anyone feel like you have some kind of comparison? Like what would we say corresponds with the face of a three-dimensional object in a two-dimensional kind of for example, how many faces does this cube have? Hmm? Six. Good. Right, so the 6 faces of a cube are comprised of what? 6 squares. Yeah, right, or walls, yeah, right? So we take 6 squares, right, and organize them into, right, this cube shape. So you could think, right, kind of like the area, right, 2D area becomes, right, a face in 3 dimensions. Does that kind of make sense to everyone? And just because we're going to kind of get into this, but hopefully everyone feels comfortable and sees how adding this extra dimension, right? How it kind of evolves, right? And so the pieces are still kind of there, and we're gonna kind of care about them, and they're gonna matter in similar ways, but kind of has this, hi Kaylee, this 3D upgrade to it. So hopefully everyone's feeling okay there. I know. So hopefully everyone's feeling good about that. Are there any kind of thoughts or comments? Is anyone confused?
So, you call the like flat area a plane?
You can think about it as a 2-dimensional plane, yeah. Yeah, so you could also think about it as, you know, your Y and your X. So, you know, your dimension of length could also be kind of like an X, right? Oriented in space, and then your Y could be the length. So then when you go into 3-dimensional space, now you have that 3rd dimension. So not only can we move vertically and horizontally, but now we can move, you know, from side to side. You think about, like, if you ever piloted a plane on a video game, right? I was trying to remember what the opposite of yaw is. There's 2 ways that you move in 3-dimensional space. Yeah, and Z is like, yeah, so you can move up, down, left, right, and then kind of, yeah, can navigate through there. So I don't know if that answered your question, Zace, I feel like I got off, but yeah, it really is just like, yeah, gonna kind of have that corresponding. Did that answer your question? Read it again. I'm distracted. Oh, plane, yeah, thank you. Yeah, so in geometry, yeah. We kind of think about these spaces, yeah, right? So if we have a 2-dimensional space, you can think of it on that flat plane. Yeah. And then in order to move it into 3 dimensions, we have to add, right, an additional plane. Yeah. Yeah, and it's got that vertical and horizontal. So really it's like when you're thinking about geometry, 2-dimensional shapes exist on this plane, just so we can work with it and manipulate. Very catchy. Any other thoughts or comments? Are you guys, hopefully you guys are on Zoom are feeling okay as well. All right, let's continue. Maybe. Okay, back to the mouse.
Look at our cube. This has a total of 8 vertices, because it has 4 at the top and 4 at the bottom. 12 edges, because it has 4 at the top, 4 around the middle, and 4 at the bottom. And 6 faces.
So hopefully everyone feels good. So for a cube, we've got 8 vertices or 8 3-dimensional corners, 12 edges, right? So the edges on the top are 4, these side edges are another 4, right? And then the bottom edges are another 4 to give us 12 total. And then we have 6 faces, right? A top and a bottom and 4 sides.
If we move the cube over, the other 3D shapes that you need to know are the cuboid, which is like a cube, but has been stretched out because it can have rectangular faces rather than all square faces. The triangular prism, which has triangles at either end, connected together by 3 edges. And then the 2 types of pyramid, which are the triangle-based pyramid and the square-based pyramid.
So hopefully everyone feels pretty good on the GED formula sheet, this thing that I'm looking at. I can't even say the name of it. Almost. Okay. The cuboid, does anyone have it for reference? So the cuboid is going to be known similarly here. So it's going to be called the rectangular prism. Yeah. So just keep that in mind, that that's what you're going to see. And then I think as well, so on, we talk about on the GED formula sheet, they have something called a right prism. You guys think that, well, no, that's all. Well, it's hard to say, depending on how you turn your head. But any thoughts on what a right prism is versus a rectangular or triangular prism? It does. And so you can see here, and I don't know how we feel, but I don't think that this triangular prism is a right triangle. It looks a little bit more either equilateral or isosceles to me. So yeah, so a right prism has, right, the bases of it are clearly right triangles. Okay. And so you should see it, it's made from right triangles. Although I'm not sure if I've ever seen a GED practice question that deals with right prisms. It's on the formula sheet though, so it's definitely fair game. And it's not too hard to deal with, but like I said, just be a little bit wary. And for me, hopefully everyone mostly thinks of what else could we call a cuboid or a rectangular prism? Is there another name you guys could, like a common name that you would think of? A bar?
How is a cuboid prism?
It's a rectangular prism.
Yeah.
Well, you can see, right, that the cube, right, all of the faces are made of squares, right? So
prism doesn't mean triangle. I mean
no.
rectangle.
So a prism basically means, and so prism is always going to have some kind of descriptive word in front of it. It's not just going to be a prism that doesn't really tell us much. So rectangular prism, right? I've taken 2 rectangles and I've basically connected them with edges, right? And so triangular prism, my bases are now triangles with these edges. So of course, a triangular prism looks like a triangle shaped crystal kind of thing, right? Or, you know, like prisms, right? Usually you're bending light.
Yeah, you can focus light through them.
Mm-hmm. And so a right prism is a triangular prism. It's just that special one. And so, yeah, usually like I just think of a cuboid as a box, right? Cubes are kind of, you know, so the faces are squares. Right, so the cube is going to have a very specific formula because all of the faces are square. Whereas, right, a cuboid is going to be made of rectangles. instead. So it's just saying the base or the faces are rectangles. Someone on Zoom thinking? Unmuted here, right here. So yeah, does that help everyone feel okay there? Kind of,
Cause like, you think like the rectangular prism? Rectangular.
I mean, once again, it could have, yeah, it could have 2 of the 6 faces could be squares and it would still be a rectangular prism. And really, right, so cute, like all cubes are rectangular prisms, just like all squares are quadrilaterals, all squares are rectangles, all squares are polygons, right? But they're very specialized. And so, yeah, a rectangular prism could have some square faces, but if all of the faces are square, then it's. Yeah. So. Yeah.
And then what doesn't.
Right, so you're saying that there's something about the dimensions of the rectangular prism are not gonna be equal, yeah. All of the sides of a cube are gonna be.
So then you could argue that the triangular prism is a cuboid, is a triangle.
Yeah, no, prisms are different than cuboids, I think, and.
Cause it's rectangular prism. So cause there would be cause when you say prism, there could be like, a person, right? Or the third one, the prism,
Uh-huh.
I see a rectangle. So I think that would be considered cuboid as well.
Yeah, and really the rectangle is just formed because we put an edge between the 2 triangles, right? So you're kind of like building like a A-frame or really it's like a tent.
Then could you like put a square on the triangle prism?
I mean, yeah, so you could have it so that these like edges are all the same. But it's still gonna be a triangular prism. What makes a prism is that it has 2 full faces that then are connected with edges. Yeah.
Is it clear? Does that have anything to do with it being a prism? Is it clear? Focus through it or no? Like that light thing we were talking about?
I mean,
It's not just.
mhm,
It's more like.
it's a
or more
category.
shapes. No, it's. Triangular, so you're. That's why triangular gives it away. Triangle.
Yeah,
or
'cause
square,
you can also have,
or
like-
hexagon.
Yep, you can have octagonal and hexagonal prisms too,
So
right?
Throw off these, tell you that there's more shapes in it besides what the name.
So I mean, what matters here is really the basic, like the basis of it. And then, the edges kind of get filled in based on how the base looks.
mirror image.
Kind of, yeah. I mean, when you're trying to draw it 3-dimensionally, and I didn't connect my edges well, but yeah, like, so really, yeah, so prism basically should signal, we always look for how is it being described? Like Tevin was saying, right? Because this is my horrible attempt at an octagonal prism, right? You could have a pentagramical or a hexagonical prism, right? And that just means that the bases are this equal shape. And then you basically put faces to connect them into the 3D. Yeah, so prisms are, crystal shapes, right? I always think of crystals when I think of prisms because, yeah, they bend light. And they're usually carved or cut in
Crystals
certain
is a
ways.
good, yeah, that's good.
Yeah, and so really a cuboid or rectangular prism is really the most boring type of prism. In that you're gonna have some kind of quadrilateral,
Fish tank,
yeah. Fish, I always think of a box, but yeah, fish tanks are cuboids. Yeah, anything box shaped books, right? Anything like that. But yeah. So a little better. So then, of course, if you look here, right, we contrast kind of our prisms with our other pointy, I guess I want to say, non-curved, right? Three shapes is that we have pyramids. And so once again, right, you can have two different bases on your pyramid. You can have a pyramid with a triangle base, which means, right, it has three edges. Or your pyramid can have a square or probably rectangular base,
Four-sided.
although I'm sure that's way too complicated of math that we don't have to worry about
You
it
should draw one. Pyramid
with a,
yeah, like
with
a,
a, yeah, like if you had like a. I mean, I guess.
oh, no.
I'm clearly not taking that much quality time. But hopefully everyone can see that, right? That here, right, what distinguishes a pyramid from a prism, right, is that we only have one base instead of two bases. So the edges, the faces come together to create, right, kind of a top vertex. All right,
So that little part of the point.
this would still be a vertex. So a triangle based pyramid has 4 vertices, right? And then this one has 5. Because the base makes vertices and then where it comes together.
So I would think that would be like off the base vertically. And that's
Pardon?
like the base, right, the bottom base.
Mhm.
That would be part of the base vertically, and then the top would be part of
It's possible. I don't think we luckily have to deal with that for our purposes. But yeah, because once again, right, there's a lot at play with angles and stuff like that. But generally, I don't think
we
we
all just. They talked about in the beginning, like the textures, the edges, the faces, we're looking for three things, you know?
Mhm.
Maybe that's what make the shape.
Yep. I like that too. Any other thoughts, comments? Thank you guys for engaging. Hopefully this is helpful. All right. Continue. Oh, wait, no. Wait.
And they're called this because they both look like pyramids and have either a triangle or a square at the bottom. Also, one thing to point out is you might sometimes hear the triangle-based pyramid being called a regular tetrahedron. But this is just a special case of a triangle-based pyramid. Then the last 3 shapes to know are the
Yeah, here's another like 3-dimensional term. And like, yeah, it's once again, like when you think of like geometric shapes that maybe aren't necessarily prisms, but we don't have to know this word for our purposes, unfortunately, but that would probably be another part of math that, yeah. Because you're building like fractals and stuff.
the sphere, which is like a tennis ball or a football shape, the cylinder, which is like a can of Coca-Cola, and the cone, which is like an upside-down ice cream cone.
So hopefully you guys can see why, right? They were kind of introduced in the order that they're introduced in. And hopefully kind of the categories are making sense, right? We have our prisms, our pyramids, and then kind of our circle based 3-dimensional shapes. Okay, and we'll get more about it. But hopefully you guys can see that basically, right? A cylinder is a prism with circles for bases, right? And then it's kind of like one curved edge is what they call that. So it's like one face and one edge there.
Before we finish,
Pardon? No, it's not curved. Well, itself isn't curved, but in order to write, once again, connect the circles, you can't use edges like you can in your prism, so it just becomes circular. So I guess it's not really curving the plane or anything. It's just trying to wrap around the circle, maybe. All right, if I missed you guys in the chat. That looks like everyone's doing good. All right.
I just want to go through cylinders, spheres, and cones in a bit more detail. Specifically, how many vertices, faces, and edges they each have. If we start with the cylinder, these have no vertices because there's no
Oh, okay. Never seen that on full screen before.
pointy corner bits. They have three faces, a flat. They have three cylinder. These have no vertices because there's no pointy corner bits. They have three faces, a flat one at the top, a curved one around the middle, and another flat one at the bottom. And then they have two circular edges, one around the top and one around the bottom. Then moving on to the sphere, this has just one single curved face that stretches around the entire shape. So it doesn't have any vertices or any edges. And lastly, the cone has just one vertex at the top, two faces, this curved one around the middle and this flat one at the bottom, and just one edge that circles around the bottom.
Hopefully that feels okay, and mostly it's making sense. So our cylinder, right, there's basically no corners, right? And that's how we know that there's no vertices. It has three faces, a top, a bottom, right? And the curved middle, and then two edges, right? The edge formed by the top and the edge formed by the bottom. Sphere, hopefully everyone can see how it does not have vertices nor edges, right? Basically a ball. And of course, once again, you could warp the shape of the ball, and that affects how you would have to do measuring or calculating on it. But luckily here we're talking about just a nice ball. So bubble. And then the cone has a vertices, right? Just like basically it's a pyramid, right? With a circle base. So you have your vertices, two faces, right? The base and the part wrapping around, and then the one edge by the base. And so usually in my experience of GED practice questions, cylinders generally the star. But sphere and cone are on our formula list, so fair game. Maybe.
Anyway, that's everything for this video. So if you'd like to practice questions on this topic or anything else in science or maths, then head over to our website by clicking the.
All right. Okay, so I just wanted to start off with a little bit of an intro just to kind of get us going. And I think especially when we move into 3D, it's helpful to have like videos and animations, because clearly I'm not the best 3D people. But I did want to, before we hop into our lesson, I did want us to look at this. Can you folks on Zoom see what I'm showing? I'm just gonna reshare because I know sometimes when I share the screen on a video sometimes. All right, and hopefully everyone was able to sign in. Let me know if you need the sign-in sheet. What am I doing? Am I back in? All right. So this is our GED formula sheet. You will have access to this on the test. I can't remember. I wish Mary was here. I don't know if they'll give you a paper copy if you choose to test in person, but I definitely know if you choose to test online that you can only refer to the online version, which just means you have to like click it open I don't know, it's not the most nice thing, but just like, right, with our two-dimensional formulas, okay, that are gonna come into handy, we're basically gonna use the same approach with our 3D shapes when we encounter a problem, right, or a problem associated. I'm very distracted. Okay. So just so everyone knows, so there's two types of formulas that you need to do various calculations on three-dimensional shape. So there's two kind of similar, right, where we have area and perimeter, right, are two measures of two-dimensional shapes. Three-dimensional shapes, we're going to be asked to either calculate the surface area or the volume. Okay, those are our two units of measurements, okay, associated with our 3D shape. So hopefully, based off of our little intro video, these 6 shapes feel good to everyone. All right. So hopefully everyone feels good about that. Please do note, okay, small e, like you see in the prism. And I think we'll have to ask Mary, pretty sure that based on what I'm seeing here, I feel like this is going to be a triangular pyramid, but it might work for both. I'm not sure. But hopefully everyone feels good about the other pieces, right? Everyone feel good about what L means, what W means, what H means. Hopefully, length, width, and height, right, are 3 dimensions there. So if you see that in your formula, hopefully you know what to look for there. Okay. Right, our friend pi is making an appearance. It's doing the same job as always. So whenever we see pi in our formula, we just need to replace it with 3.14 to do our calculating. Sorry that this. Hopefully you guys can see me. Okay. So hopefully everyone feels good about that. So here are, right, our surface area formulas. So those come first. And so it's kind of funny that they split these two out, and then for the 3D shapes, they just make a table. But hopefully everyone can see that the middle are the surface area formulas, and the far right are our volume formulas, okay? And then, like I said, hopefully when you look at the variables in there, they shouldn't be that brand new, except for a few. So length, width, height, okay? Capital B, right? It means we're referring to the base, okay? And I think it's the area of the base, yeah. Okay, so capital B is the area of the base. Hopefully that makes sense, right? If you have a prism, we need to know, right, the area of the two bases plus the middle part, right? So hopefully that makes sense. So P equals perimeter of base with area B. Okay, so hopefully that feels okay. And then hopefully you notice as well, right? Cylinder, cone, and sphere, right? Our friend pi and our friend r, radius, are making an appearance, okay? So they're gonna come right back to us, okay? And so hopefully you can kind of see, maybe not necessarily with perimeter, but we did, well, right. But basically, right, we talked about area is our, right, measurement of two-dimensional space. That means, right, square inches, square feet, square kilometers, square meters. Okay, and then, right, volume basically adds that third dimension. So once again, right, if you look at the area of a rectangle, the formula tells us it's length times width, right? And so to calculate volume, we just throw in that third dimension of height. So hopefully you kind of see how these build on each other. It's not on here, but right, the area of a square is S squared. So what of a cube, of a cube? S cubed, right? S times S times S, because you have your three dimensions. And so you'll see some of these two-dimensional formulas, some of our, what am I trying to say? Parameters are going to be the same, right? And we're going to use some of these in here. So hopefully that feels like a good preview. And I just wanted everyone to kind of see where we've been, okay, and where we're headed. And so, like I said, very similar to kind of the area problems that we ended on last week. They really love to give us problems where, once again, we might know the volume, but we might not know one of our three dimensions. Okay, so we have to use that to then solve. So that these formulas are going to be important, and definitely the way they're going to test your knowledge. Okay. Any other thoughts or comments, concerns? Okay. Hopefully everyone's still hanging in there with me, all right? I'm just gonna, just in case, grab this for you guys. Just see that we've got some folks on Zoom. Good. Thanks, Latanya. Yeah, I know it's kind of a lot. I kind of gave us a big bite, but we're gonna now just nibble, okay? But I thought it might be helpful to kind of get in. Just in case anyone needs it, I did put the sign-in sheet in the Zoom chat, so feel free to please click on that, fill out that form, but 3 p.m. is your time out. Okay. So I sent this out on Remind earlier. This is also on Canvas. Let's see if I have a copy for students. Close that can. I know it's big. I think there's a lot on the pages. But yes, and it's got the answers in the back, so you're always welcome to like work ahead. Let me go ahead and put it in the chat for you folks on Zoom. Like I said, it is on Canvas. If you have access to that. If you don't have access to that, if you don't know what I'm talking about, please message me and I'll try and get you hooked in. Mm. All right. But we've already kind of done the first few pages, just when we kind of went through the introductory video. But like I said, it's always helpful to kind of have this down clear in your minds. So so solid figures, three-dimensional figures, all kind of potato, same things. Hopefully those make sense to everyone. And oh, the other reason they're so fat is I didn't double side. I didn't tell the copier to double check. That's why that was the part. That was a bad. All right, so you can always kind of think of a solid figure or a three-dimensional figure, right? So they like to use this idea of it takes up space. Just any physical thing, right, in our world. You can see, touch, and pull solid figures. And they kind of give us the four main ones. It's kind of funny, right? Because every book and every video and everything is going to have a little difference. So for GED, we have 6. Here we have 4. However, right, we know that these are kind of the same category, but these are probably the stars for sure. And so the first one is our friend, the cube, kind of the easiest one, right, to deal with. And so equal length and each pair of sides forms a right angle. And that's each face of a cube is a square, right? We've already. All right. So rectangular solid, right? Rectangular prism. They don't like to call things the same name, but they are the same thing. So once again, if you see that word solid or prism, there should be a descriptive word in front of it telling you what the base is made from. So you actually know what kind of solid or what kind of prism you have. Okay. So once again, at each vertices, you're forming pairs of right angles. Cylinder, right? We talked about this. Basically, our can shape. Remember, top and bottom are circles, okay, parallel to each other, which is probably another one of those, like, you know, if you wanted to not make them parallel, then that would affect our math. And we don't have to know that yet, unless you really want to. And then the important thing here is, right, that the distance between the top and bottom is the height. Okay. When we have a cylinder, and you can see this in the formulas, if you look. Right? Pi r squared, right? That's our circle times the height. Okay. Or if you look at the surface area of a cylinder, 2 pi r squared, right? That's the area of the top and the bottom, and then you need the height for the other. Yeah, so height, or this variable of h, is going to be necessary to work with cylinders. So yeah, so this is the other important dimension of a cylinder. The other important thing, right, is that since you have a circle, you'll need to know the radius of the base. All right, and then finally, our cone, okay, has the base. And then the vertex. And similarly, right, you know that the distance from the center of the base to the vertex is the height of the cone. So once again, when we have these cylinders and cones, right, we're adding this dimension of height. Okay, we have two circular bases or just one circular bottom base that's coming out to you. Okay. Everyone hanging in there, all right? Okay. So page 2, I don't feel like we need to worry too much about this, although it's kind of funny that the pile of sand is, you can't see it, but hopefully everyone feels like you could, right, label these ones, yeah? Do we need to do it, or is it helpful?
Everything's helpful.
All right.
Gotta learn the easy stuff if you wanna,
True.
yeah, if you wanna like. Do the harder stuff. Baby steps.
Mhm. I love how they say like ice cream cone, then what is it? But yeah, I mean, it definitely is gonna come into play because you might not get like a picture or figure, so yeah, sometimes you might see something like a grain silo or a cylindrical water tank, right? So you have to definitely make those connections. So books and cereal boxes are rectangular solid. I'm just abbreviating rectangular because I don't want to write it out. Oh, I just about to write dice. Ah, that's funny. I'm like, this is a die, which is a cube. So once again, right, if you have more than a 6-sided dice, right, the faces make it look more and more like a circle, like a sphere, right? Ice chest, I guess there, freezer box.
Into the pipe.
I know, you can kind of see, I can kind of see a little bit, but anything that's a pile of sand or gravel is gonna be a cone. So it's supposed to be like a, you can kind of see it. Party hat is also cone. File drawer. So hopefully everyone got those down, and yeah, I would definitely say it's at least helpful because yeah, sometimes you might not have the picture. So you do once again have to kind of use the question to help you figure out what shape do I have?
So what shape is a pile of sand?
It's a cone.
Oh, it's a cone?
Yeah, so basically kind of think about like a, what's it called, the hourglass, right? The sand falls through it, it forms kind of like a cone shape. So yeah, usually it's gonna be like you have a this big of a pile of sand that's this tall. And just know that they want you to use cone formulas. All right. Oh. Continue on for a little bit. We're about to take a break, but I think we can go a little bit more. Okay. So hopefully everyone's feeling good about how, right, we started in kind of this one dimension points, right, lines. Then we began to connect lines to create 2-dimensional features like polygon figures, like polygons and circles. And so by adding this 3rd dimension, right, we've created a 3-dimensional figure. And so now we have our 3 dimensions, and sometimes you, if it's helpful to think of height as like depth. Like. I don't know. And so we already talked about this idea of faces, okay? And so of course, faces are going to be our polygons. Okay, that create the sides of the figures. And so the first and most common way that we measure or account for the space taken up by a solid figure is with a measurement of volume. Okay. So whenever you think about how much can something hold, right? You're asking how much volume, right? Can it take? Cups, tubs, like stadiums, planes, right? Train cars. So volume is a measure of how much a solid can hold. So volume tells how much water a pool holds or how much air is in a room. Okay. And we know that depending on the size of the pool and the shape, right, it will contain a specific amount of water. When we exceed that volume, what's going to happen to the pool? It's going to overflow. Yep, exactly. Because we've exceeded the volume. Or if you're making lots of splashing waves and playing water. Decrease the volume of water in the pool. But good. Hopefully that feels good to everyone. So it's kind of funny that volume's kind of on our outside. But it really is probably the most common 3-dimensional. So because of that, right? We measure volume in cubic units, just like area is in square units. Now that we're on 3D, we're on cube, okay? So a cubic foot is 1 foot long, 1 foot wide, and 1 foot deep, right? So if you're buying a cooler, it'll tell you, right, the volume probably in cubic inches or feet, depending on the size. You might see it as inches cubed like that, right? Inch with the superscript 3, or they might have it abbreviated like this. Can't remember. I don't think it's going to be too important for us, but once again, if you notice in your answer, oh, the units are cubed, am I dealing with a 3-dimensional shape? Okay, probably yes, unless you have cubes and squares and singulars, then hopefully that might maybe answer too. So for our rectangular solid, right, our box, our rectangular prism, and also even a cube, okay, the formula is that the volume is equal to the length times the width times the height, right? It's really just that 3 dimensions. Okay, we're adding 1 more dimension on top of area. Okay. And so of course, in order to calculate it, we need to have measurements of those 3 dimensions, and then you just multiply them together. So it's pretty easy calculation, at least for this shape. Okay, so go ahead and find the volume of these 3 figures. Should go pretty quickly, and then we'll take a break. You guys got them? Hopefully went pretty easily and quickly. One more minute. There you go. Okay. So really fast, hopefully. What is the volume of our figure for number 1? Okay. Does everyone like that? 240 what? Cubic meters. Good. How about number 2? Okay, I heard 30 at first. 38 cubic inches. Good. And then number 3?
Are you going to write the formula?
Yes. Sure. I'm not showing my work is what you're saying. Length times width times height. Length. So for number 3, I'm getting 56. Does that about sound all right? Cubic inches. Hopefully that feels good for everyone. All right, let's take a 10-minute break. So 2:10, we'll come back and continue onward. Hopefully everyone on Zoom is hanging in there okay. Let me know if you have any questions or need anything, access to anything. Okay, guys, hopefully you were able to give your brain a little bit of break there. So continuing on, so this is our, I think, the fourth page. So just continuing on. So a cube is a solid whose faces are all squares. We learned that already. So our formula, this is not on, right? Our formula sheet, but we can use our rectangular prism formula and get the same thing. But for a cube, volume is equal to the length of the sides cubed. Good. Okay. Because we have our 3 dimensions. Okay. And so because these are all squares, all the sides are equal.
We get a packet from you.
Actually don't have another one. Let me print that out. I know. It's a lot. I'm sending that out to the other machine. Brendan, right?
Yeah.
Cool. I'll let you guys work on that. You can go ahead and do part B, those 4 problems if you want. Should be pretty straightforward. You ready?
Should be. Yeah, if you want. Simpler than everything else. It's all the way to the. One more. I'm gonna be time, all right, about 6. 28.
Yeah. About 7. About 8.
So,
Yeah. About 9. There's 2 different ones and it's like he's asking me
215, 192,
216.
216, 192. That's it. That's where I'm at.
Hopefully everyone is feeling okay. So we have this small cube shaped refrigerator. One side is 2 feet, which means all sides are 2 feet, so 2 times 2 times 2 means that has a volume of 8 cubic feet. So we just do the same thing, right, with our cubes here. So what's 5 cubed? Fully 125. Number, oh, centimeters cubed. Number 5 should have been pretty easy. 1 cube is 1. What's 12 cubed? I can't do that one. I don't remember. 1,000 what?
1728.
Thank you. Sorry, my ears are broken. So 12 cubed gives us, yes, 1,738 cubic. Is everyone feeling good? Shouldn't be too terribly crazy yet. Okay, so then we might see some problems like this. So go ahead and work on 7 through 11. Okay, you're welcome to talk to people that helpful. And hopefully everyone sees, right, that this drawing goes with 7. That or verbally or over that, if and or when you're ready to talk about these Still working a little bit, wanting more time. There you go. Okay. Alright, hopefully these felt pretty doable. Just what we've been doing already, so they're giving us our 3 dimensions and just asking us to calculate the volume. So for number 1, 40 times 20 times 2 to 160 cubic yards. Does that sound good?
Forty times 20 times 2?
You getting a different number?
116?
Me
One
times,
thousand.
Yeah, 1,016.
oh, 1,600, thank you.
40 times 20,
Sorry. Yeah,
40 times 20.
thank you, that's much better.
Times 2.
Sorry, I lost one of my pin spots there, fired in. So then number 8, I see 6,000. So 30 times 20 times 10. Should give us, hopefully that's ample air, I have no idea. Feels like a lot. Feels like a lot of space. Alright, how about number 9? Which of the 2 packing crates can hold more? The first one? Why? So you're saying the volume here is larger than the volume here? Good. So what's the volume of the cube?
It was 216.
Versus what about the rectangular? 119? Oh, thank you, sorry. So what if they did have equal volume? Then which one could hold more? True, exactly, right? Yeah, yeah, it depends, but if their volume is equal, they should be able to technically hold the same amount. But yeah, it all depends on if it's like liquid or sand or something like that, right? That's gonna fill the whole space, then
I think that would be the same.
No idea. I got 3. You'd be missing out on the extra.
yes, you would not be being efficient with your space. With your
Then you'll
package.
have that.
Yep. But really, if they had been equal, we would have just said they can technically hold the same. Right, but then of course, it would definitely depend on what we're trying to pack into those 2. Good. So then number 10, the volume of the concrete sidewalk. So hopefully everyone felt like you could still do this with your calculator pretty easily. Right, let's see, 16 times 4 is 54, is that right? No,
Then you do that one.
what'd you do?
It's smaller.
Oh, you just halved 4? That would probably work a lot easier. Yeah, 32.
I got 30.
32.
Yeah, I was just going the other way. I was doing 16 times 4 divided by 2. But good. Or, right, you can always substitute 0.5 in your calculator too, right? And you can do 16 times 4 times 0.5. Is everyone feeling okay about that one? So just, yeah, don't let that fraction scare you. You could type it into your calculator if you want, or you could do it first, 4 times. Can do it, right? You can do a fraction. 1/2 times So it does work in your calculator, it takes a little extra numbering. But you could also, yep, you could just do it in parts, and oftentimes, if I can easily convert this fraction to a decimal, then it makes my calculator easier to plug in. All right, so then what happens to the volume of a cube if you double the length of each side? I mean, I'm assuming, and then, right, they'd want us to calculate, so. But yeah, like the size
It's like,
doubles.
and, I don't know.
Almost, yeah.
Like adding a fourth dimension.
Cause yeah, so basically what you're seeing here is when you multiply. Like when you double it, you're basically. To get from here to here, you're multiplying this times 8. So just basically, right, two cubed is 8, right? 27 times 8 is 216. So when you double the value of your side, you basically are. Yeah, like doubling the volume. Across those 3 dimensions. So yeah, it is kind of like you're doubling it, I think.
It's like,
Mhm.
oh, it's 3 inches. Your jobs. Then you 6 to the 3 inches. You're just adding another. Gives you 6. And
Yeah, and let's see, 3. What's 3?
I,
you don't take
3,
Cube.
that's the third.
so a cube, all sides are all in the same. 3 just basically changes.
Yeah, if I double the size.
You're just doubling your 3 inches.
And basically, right, you're doubling it on all 3 dimensions, which is the same as multiplying by 8. Just kind of showing you number patterns and relationships. I guess it's just, yeah, that like yeah, it's not like doubling, but when you increase the volume that much, right? It really does like double in size, but because it's a cube, it is more substantial of a doubling. I think that's what we're getting at. But I'm not sure, I'd have to actually look.
It quads it or?
because like
or
it's,
equal?
Well,
surface area is like increased dramatically compared to the smaller cube.
yeah,
Because like the ratio is not.
We're like still working with like, right. And that's what we're trying to do 3 times, so we already know the size of equal. And it only gives you 3 inches, so it doesn't give us like 3 inches, that's a 3, and then. It's like the width, it's like giving you 2 inches. Like, you just did 3 inches, you double it 3 times 2 is 6. And then the 6 to the third gives you 216.
God, does it.
it would be 3 inches lane, 2 inches width. and
Oh, okay,
Yeah,
I think I get it now, because you're timesing,
Yeah, double, right,
well, I guess you would call it, you're adding physical. Same value,
yeah.
Mhm.
Always up. You know, like certain length, certain width, certain. This one just gives you 3 inches.
and like I said, I just want you to see that, yeah, right, by doubling your dimensions, it dramatically increases the volume. Right, number 4,
Far out.
4. Everyone's feeling okay? So. Like I said, we've seen this information before. Maybe another kind of helpful way to visualize some of this. Okay. So like our other, right, calculations, measurements that we can do on things. Right, we know that there's going to be a formula associated with it. Okay. And so of course formulas make our lives easier, especially when our shapes get funkier than cubes and boxes. And so, right, we use volume formulas the same way we've been using all of our other formulas, right? We're going to plug in, right, the values or dimensions that we know into the formula and then calculate it, right? And then just remember, right, that you can recognize, right, a unit of volume because it's in cubic something, okay? And then I think all of the like gallons, quarts, pints, those are also measurements of volume as well. That's why you have cc's, right, at a hospital or actual cubic centimeters, Mhm. Right, of however much they put in the syringe. All right, so just another way of kind of maybe conceptualizing what we were seeing before. So we know that the volume of a cube, we, right, just take the length of the side and cube it, multiply it by itself 3 times. So pretty straightforward, shouldn't feel hard or scary. Go ahead and jump to the next page. If you need to do 1 through 3 just to practice, you can. But what I'd like you guys to work on is 6, 7, and 8. Focus on those. when you think you have these three ready. And then if you want to go back and look at the previous 4 questions. These look more. I'm gonna see. Everyone doing with these ones, all right? Basically, you're just kind of adding potentially another step. Okay, still need a little more time. No worries. Right, even if you didn't get all the way through these problems, hopefully you at least feel like you could get started on them and knew what to do. So oftentimes, right, you see these kind of two-step problems where we'll need to calculate something and then, right, use that to do something else. So number one, kind of look, or sorry, but hopefully it turned out well. So a water storage tank in the shape of a cube measures 1.4 meters along each edge. If 1 cubic meter of water weighs 1 metric ton, how many metric tons of water can the tank hold? Does anyone feel like you got an answer there?
Yeah.
So, yep, so calculate the volume of the cube. So I'm just gonna go to 2, well, we can use all 3, might as well, right? So we know that the volume of the cube is, right, 68.921 cubic meters, but the question's asking us metric tons. So what's our ratio here? I mean, I wouldn't round if they're giving you an exact figure. But what this is telling us, right, is that 1 cubic meter of water equals 1 metric ton. I have no idea how to. So, right, so this measurement of volume is equal to this measurement of weight. So we have a 1-to-1 ratio here. So if we know how many cubic meters we have, right, how many tons is that? Exactly. Oh, thank you, Patrice. Yeah, I forgot after break. Thank you. That's what I wasn't doing. Good. So like Zasis is saying, because we have this 1-to-1 ratio, then we know that it's basically still 1-to-1.
So it's still 68.921.
It's just a really fun.
Yeah.
Yeah. So potentially, right, if they had told us like 3 cubic meters to 1 ton, then we would need to divide by 3, figure out the conversion between.
Be 69.
Yeah, you could round it up.
Don't you also calculate? The density of water when it's on top of each other.
Yeah,
So then we're like, well, it is technically capacity.
right. The volume is, yeah, that measurement of capacity, but the density of the material that you're putting into that space could vary, and volume is part of calculating density. So to figure out the density of something you're looking at, it's the volume that it's occupying times its mass. So if you have small volume and high mass, then it's very dense, very heavy.
I know like the deep on the ocean,
Mhm.
the pressure difference between above and below.
Oh, right.
So they would be like, they would do like a slight calculation.
Right, yeah, so based on the depth that you're going would affect like how you would mix your oxygen. Or how you need to ascend, right, to make sure you don't get and stuff. Yep. Yeah, so there could be metric tons of water.
So is this like in a vacuum?
Yeah,
Be like no gravity, no
yeah,
in the middle of it,
yeah,
nothing but fighting.
yeah, this is all very experimental. Yeah, we're not having to. Yeah, worry about those extra potential factors that matter more, yeah, when we're doing more precise or more physical science.
But the looks on our faces, that's what makes them.
What's the deal with the water tower too? It was also water tower.
Oh, right, yeah,
Did you figure that out?
Yep. To figure out how strong they need to be.
Water flows down, because it's on top of the tower.
No, and that. We live on a mountain.
Oh, yeah, that's true.
Living on.
Yeah, the air is more densely packed.
Air is better
It's thinner.
quality up here, but it's easier to breathe down in
It's
Phoenix.
less oxygen rich.
Yeah.
Yeah.
That rocks.
So yeah, so volume isn't necessarily the weight. But sometimes you get that straight conversion. Okay, so then number 7, the deluxe calculator company packs calculators in cubicle shipping boxes that are 2 feet on each side. How many shipping boxes can be put in a moving van that has a packing volume of 896 cubic feet?
Well, in theory, it's 112 calculators.
The shipping boxes.
Or the shipping boxes.
The box.
Yeah,
So
but I don't know, like, if it's like a square van
Yeah,
or, yeah, like pretty.
I mean, I guess since they're calling it packing volume, they're
Yeah,
saying
volume.
like this is the capacity.
Well,
But I mean, even then, yeah.
yeah, it's like.
No.
112 shipping boxes,
But yep. And how are you guys getting 112?
896 divided by 8.
Good. So we know that each box, right, has a volume of 8 cubic feet, right, which is 2 times 1 times 2. The dimensions of our box. And if we have this much total volume, right, then we take the total 896 and divide it by our single volume. And so, yes, we know that in theory, if our packing volume is shaped correctly, we should be able to get 112 boxes in the van. Although that's still. Yeah. All right. Simon's Toy Company makes plastic blocks that are in the shape of cubes, 3 inches on each side. How many blocks can be put in a cube-shaped mailing box that measures 15 inches on each edge? 125 blocks. Okay. How did you get that number?
Or, no, I-
So we know that the volume of 1 block, right, is 27 cubic inches, right? And then we know that the mailing box, what is the volume of the mailing box? And so same, right, same calculation we did previously, right? We take our total volume and divide it by our partial volume, right? So this is the part that we're gonna fill up here, so, and I'm sorry for my shiny pen. 3375 divided by 27. Whoa, oopsie doodle. Love it. Let me try one more time. Yeah. Good. So each box can contain 125 blocks. Box per box. Is everyone feeling good about these problems? Knowing what to do? Good. Definitely pretty common. All right, so the next page is breaking down our rectangular solid / prism / box again. Hopefully everyone's feeling good about that. I'm not sure why they want to call it a. And so pretty straightforward. I think we've done pretty well. If you need to practice, you can do these 3 at the bottom, but let's once again jump ahead. So yeah, even these 10 problems seem pretty straightforward. Okay. Just multiply your 3 dimensions, right? Okay, so I think we'll go ahead and be done 6 minutes early today because I don't, I feel like we're gonna have to spend a little time in our cylinder. So, like I said, if you want to go back and finish those problems we jumped over today, you're welcome to. If not, we'll pick it up here on Wednesday, all right? Any final questions, comments, concerns, thoughts? All right, well, thank you guys for working hard today. Hopefully feeling good about this final bit of job.
All right, man. We're gonna bump you up. Good. That's later.
We're doing good, Kaylee?
Yeah, I work with, I know this.
Good.
But, how do you convert, what was it? I didn't find it.
Okay. Is it like yards to feet, inches to feet?